Hello everyone, I am Xinwei. Today I will present Witcher systematic crash consistency testing for non-volatile memory key value stores. This is a joint work from Virginia Tech and Stony Brook University. First of all, I'd like to give a summary of this work. Non-volatile memory enables writing crash-consistent programs without paying storage overhead. However, writing crash-consistent program is error-prone. Each existing NVM bug detectors either use exhaustive searching to enumerate all possible crash states, which is not scalable, or use user-provided oracles to validate the inconsistencies, which requires manual efforts. The proposed work, which targets NVM key value stores, is use inference of likely correctness conditions to prune test space to achieve scalability. It uses validation with output occurrence checking to validate the inconsistency automatically, which were detected 205 correctness and performance bugs in NVM key value stores and the PMDK library. 149 of them are new bugs. This slide shows the outline of the presentation. We will present the background and the motivation first, then we will present the design of the feature. After that, we will present the evaluation of feature. At last, we will make the conclusion. NVM has been considered to revolutionize the storage stack by providing the following properties: persistency by the adjustable, low latency, and high capacity. However, NVM programming is hard because you must guarantee the integrity of your data even under power failure. Formally, a crash-consistent application can recover a consistent state from persistent memory in the event of a crash like a power failure. In the current architecture, a cache is volatile. Volatile cache states may be lost upon a crash. So controlling the durability and the ordering for cache lines is the core in the NVM programming. To support NVM programming, Intel provides two primitives for controlling cache line eviction. Once the data is evicted from the cache, it becomes persistent. The first primitive is flush. It writes back a cache line from the cache to memory. The second primitive is fence. It provides ordering guarantee between flushes. Let's have an example here. After the first line is executed, x equals 1, reach the cache. Then a flush is executed. It issues a write back from the cache. But after executing the flush, x equals 1 is not guaranteed to reach the memory. Only the following fence is finished. Then x equals 1 reach the memory and it becomes persistent. Then y equals 1 has the same flow here. So by using these two primitives, NVM programs eventually control durability of updates and ordering of durability without unnecessary persistent overhead. We did an NVM bug survey on open source NVM software. There are different persistence bugs here. Persistence ordering bug, fail to enforce that A must be persisted before B. Persistency atomicity bug, fails to enforce that A and B must be persisted together. Persistency performance bugs such as extra flush and extra fence. Among those three bug types, let's dive into details of the persistent ordering bug and the atomicity bug. The persistent ordering bug, which is caused by incorrect persistent order. I will use a real bug example to illustrate it. The bug comes from a persistent hash table called level hash from OSDI 18. For each key value pair, it has a valid flag called a token in this persistent hash table. If you look at the code at the left side, which is the insert code, the write key, value, and the token, and then call flush and fence to persistent token, key and value, and then the token. So it looks correct. It persists order writes in the same order as the writes happened. However, it may incur a problem. I will have an example here. So after executing the first three writes, it is possible that the token is evicted from the cache. If there's a crash happening then, after recovery, only the token is persistent, but the key and the value are not. If you look at the read code, for a reading, it checks the token to be valid first, then compares the key and returns the value. So users may read garbage value in this example because the token is persisted, but the key and value are not. The root cause of this bug is the incorrect persistent order. The red figure shows the fix. It first writes the key and value, then persists key and value. After that, it writes token and then persists the token. So in this way, when token is persisted, the key and value must also be persisted. Here, I need to emphasize that it requires application-specific knowledge to detect such bugs. So the persistency atomicity bug, which is incurred by incorrect persistency atomicity among multiple updates. Let's use the level hash example again. The code snippet is from an update operation. An update operation is to update an existing key with a new value. So in this code, it uses out-of-space updates. It writes a new key value pair and a token to a new location first, location Y in this example. Then it invalidates the old location. So X in this example is the old location. Then it persists a new key and value and then persists the tokens. The code will incur a problem, and I will give an example. Suppose at the very beginning, the old key and value and the token are persistent in the NVM at the beginning. After writing the new key value and the token, it is possible that all of them get evicted from the cache. If there is a crash happening then, after recovery, the key has both the old and the new values. So the root cause of this bug is that writing two tokens is not atomic. The red figure shows the fix. It first writes the new key value, then persists the new key value. After that, it updates the two tokens in a single 8-byte write, and then persisted the tokens. In this way, two tokens are updated in an atomic manner. Again, detecting this bug also requires application-specific knowledge. To detect persistent bug, previous works use either exhaustive searching or user-provided oracles. Exhaustive searching means that it will check all possible crash states. The benefit of this one is no false negative because it searches every possible cases. However, it is expensive and not scalable at all. To reveal a bug, it often needs a long execution. We will show the experiment to prove this later. In our experiment, we need to spend more than months to explore all possible cases of 2,000 operations. User-provided oracles require users to provide any kind of guidance to tools to validate a bug. The benefit is to make the validation process simple, just checking the rule provided by users. However, this solution needs manual efforts, which is error-prone, especially for dividing application-specific oracles. This motivates Witcher, which use neither exhaustive searching nor user-provided oracles. We just presented the background and motivation. Now we are moving to the design of Witcher. So the first challenge here, how can we prune the test space without the user-provided oracles? To address this, we propose likely-correctness conditions inference. Our key observation is that programmers often left some hints on what they want to ensure in the source code. Take the read code example again. The hint is that it checks the token first, then reads the key and the value. More specifically, there is a control dependence between token and the key value. This tells us that when the token is valid, then the key and the value pair must be persisted. So the correctness condition is that persisting key and value should happen before updating the token. Having this inferred likely correctness condition, we will only test the crash states violating it. Take the right example here again. We apply the inferred likely correctness condition and check whether there are violations. And we found that the token can be persisted before the key value pair, so that we will test the crash state where only the token is persisted. In this way, which will automatically prunes the test space by inferring likely correctness conditions. Suppose we found a potentially crash inconsistent NVM state using the first key idea. The second challenge is that how to automatically validate the crash state. To address this, we should use output equivalence checking by leveraging durable linearization. Durable linearization means upon a crash, an NVM program should behave as if the crash operation is either all or nothing. Let's use an example here. Suppose we have a crash execution. It has 3 operations: insert key with value 1, delete key, then insert key with value 2. The crash happens at the 3rd operation. All semantics means that all those 3 operations have been successfully completed. Nothing semantics means that the first 2 operations have been successfully completed, but not the 3rd one. Instead of comparing those images, we run each image with the same test case, which is get key operation in this example, and then collect outputs. Based on durable linearization, a consistent output should match either value 2 or none in this example. If the testing output matches neither of those 2 outputs, such as value 1, it indicates that there is an inconsistency, thus a bug in crashing operation. In this way, which will automatically validate the crashed state. Based on those 2 ideas just presented, we designed Witcher, a new systematic crash consistent testing tool for NVM key value stores. Witcher takes a program and a test case as input. A test case is a sequence of program operations. The first step is to trace memory accesses. Then Witcher infers likely correctness conditions from the trace by using program analysis. After that, Witcher constructs a set of crash NVM images violating the conditions. Then Witcher performs output equivalence checking to validate if the condition violation is a true bug. Witcher also detects performance bugs as spawners by analyzing the trace. To get dynamic traces, we instrumented an NVM program using an LLVM compiler path and execute the instrumented binary with a test case to collect the execution trace. We trace the load, store, including the updated value, branch, call, return, flush, and memory fence instructions in our instrumentation. The process of inferring likely correctness condition is to co-locate program, correlate program dependence to NVM correctness conditions. I will give one example here. If we have code of y equals x plus 1, and both x and y are on NVM, the program dependence is that write y is data dependent on read x. The implicit correctness condition is that x should be persisted before writing y, because y is using x to update. Before writing y, x should be ready, thus persistent. We inferred our likely correctness condition that persistent x happens before write y. Having this condition, we will only test the crash state that violates the condition, which is y is persistent, but x is not. Which means after recovery, y is the updated value, but x is still not updated, leading to an inconsistent state. Here, likely correctness condition is not necessary to be true because we will have a validation process in the next step. We have 4 likely correctness conditions in total. First one is a data dependence implicit implies persistence ordering. Second, control dependence implies persistence ordering. Third, a guarded read implies persistent ordering. Last, guardian implies persistence atomicity. I cannot present all of them in this presentation. Please refer to the paper for more details. To infer the likely correctness conditions, we should perform the program dependence analysis to infer likely correctness conditions from the source code and the execution chases. We use a mix of static and dynamic trace analysis. When instrumenting the source code for tracing, we perform static analysis to capture register level data and control dependence. Then we extract the memory level data dependence by analyzing memory level data flow in the collected trace. The next step is to generate a set of crash NVM images that violates the correctness conditions. There are two questions here. The first one is how to guarantee each crash NVM state is valid. Here we use cache and NVM simulation to generate only valid NVM states that violate the likely correctness condition, but still obey the semantic of a persistency control at a cache-like granularity. Starting from the empty cache and the NVM states, we simulate the effect of store, flush, and fence instructions along the trace while honoring the memory model of a processor. And the second question is how to detect the violations. During the simulation, we check if there could be an NVM state that violates a likely correctness condition before executing each fence instruction, because the fence ensures a persistent state change. Okay, we have just presented the design of Witcher. Now we are going to present the evaluation. So our evaluation aims to answer the following questions. First, how can Witcher detect new bugs? Second, is Witcher scalable? So we evaluate Witcher with 20 NVM applications, including 5 highly optimized persistent key value indexes, 7 concurrent persistent index converted by recipe, 6 Intel PMDK applications, and 2 PMDK-based server programs, memcached and Redis. Those applications have diverse implementations, including using low-level persistent primitives and high-level persistent transactions, and single-thread, log-based, log-free in terms of parallelism. And we run NVM programs with a test case consisting of 2,000 randomly generated key value operations. We found that 2,000 operations are large enough to achieve reasonable and stable code coverage for our tested NVM programs. In summary, Witcher detected 47 correctness bugs from 18 programs, and among them, 36 of them are new bugs. There are 25 ordering bugs and 22 atomicity bugs, and all the bugs were confirmed by the developers. The detected bugs has diverse impacts such as loss, unexpected duplicated key value pairs, unexpected operation failure, and inconsistent structure. There are different strategies for fixing those bugs. And here, I need to emphasize that all those bug fixes are complicated and require a deep understanding of the applications. I'd like to show one new bug from the PMDK memory allocator detected by Witcher. This code snippet is from PMDK memory block management. In this code snippet, it trains the old header first and then writes a new header. However, the failure atomicity algorithm of PMDK requires that the new header should be initialized before the older header is changed. And to fix this bug, we need to flip the order of 2 function calls. And detecting this bug requires application-specific knowledge, which is able to detect this bug by using likely correctness condition inference and output equivalence checking. We also evaluated how effective Witcher can prune the test space and thus improve the scalability. First, we compare the numbers of test crash states between Witcher and the exhaustive searching approach YAT. We use the same trace with 2,000 randomly operations. As shown in the figure, the test space of YAT is several orders larger than Witcher, and we only test when there is a correctness condition violation, significantly reduce the number of test cases, yet still detecting many bugs. Second, we also compare our tool against the random searching with 100 million possible crash states. Testing each 100 million crash states costs around 1 week. The result shows that the random 100 million case can only detect 1 or 2 bugs that which are detected, which shows that random searching doesn't work. And our approach effectively detects many bugs. In the end, we will make the conclusion. In conclusion, developing a correct NVM-backed crash consistent program is hard. The proposed tool, which infers likely correctness conditions to prune test space, performs output equivalence checking to test inconsistency automatically. In evaluation, which detected 205 correctness and performance bugs in NVM-backed key-value stores and the PMDK library, which can effectively detect NVM bugs without a user-provided checker, without a test space explosion problem.